We are recording. So, today is lists day. To follow our roadmap here, so now we're gonna make list literals. Like we have three things before going full blown on the database side. So we have list literals, carrying conjunction, name spacing, and then we're gonna start introducing specific byte code, generating specific code for database support with the special syntax. But today is list literals. Lists are supported by the book, and we didn't do them before. We decided to do them now. So let's think about it. So let's read. Um,
Commit what I have before I start.
sure. Programming with linear lists being so privileged in Prolog, it makes sense to tailor the design for this specific structure. In particular, non-empty list functors need not be represented explicitly on the heap. Thus again, we define a fourth sort for heap cell tagged list, indicating that the cell's datum is the heap address of the first element of a list pair. Clearly, to respect the subterm contiguity convention, the second of the pair is always the address following that of the first. The following instructions are thus added to the party. So we have to introduce a new. Oh, actually, we also have an example here. So, for example, the code generated for this query using Prolog's launcher from lists is shown in figure 5.4, and that for the fact in 5.5. Note the hidden presence of the atom empty list as list terminator. So this is for the query, and this is for the other thing. So I guess the first thing we gotta do is introduce list as an available thing on the heap. But in order to do that, that means that our machine needs to be able to accept that in here. Manny, are you there?
Yeah,
So, do you agree with me that we need to add list in here?
constant of constant, structure of structure. Oh, those are for list cells, right?
Yeah.
No, we don't.
The book just says we do, so how are we gonna get around that?
What do you mean?
The book says that we need to introduce a new thing that in the heap cells, right? And as far as I can tell, the T is the contents of the heap cell. These are the available
Uh,
tags that we have on a heap cell, inside a heap cell.
right, because we need to put those in registers as well, right?
Exactly.
Oh, in that case, yeah, we need to have lists in registers. That is true.
There's a problem though. List is already taken. So are we going with list then?
List is already oh, for the built-in.
Yeah.
Yeah.
No, no, not for the built-in, because there's a module called list in OCaml.
Yeah, yeah, for the built-in in OCaml.
Oh, built-in in OCaml, not this built-in. Does that work? Let's actually try first and see what happens. So what I'm gonna save with that, a number, which is the address.
Uh, yeah, the address of the list.
Okay, so this is gonna be an int. Let's see if this compiles. So dun exec karuta, it does. Okay, so it is able to figure this out. So this is a list and this is an address. Um, Maybe I should have an alias to get to like differentiate. For example, our count doesn't have an address, right? What are those things carry an address? Address, right? Reference. Does the structure record an address? I don't remember.
No.
No. Okay, so now it's better.
Wait. Structure. Not functor. Structure.
Yeah.
Yeah, that does need an address actually.
Yeah. It's still an integer, but now you don't have to remember which one. Like, is this an address? Is this an address? No, this is written in code. Okay, so we introduce that. So which one we want to do first, Money? Do you want to implement these first?
Uh,
Or you want to do the parsing first?
Let's implement the instructions first.
Sure. So, that is in the evaluator. And no, let's put them before the gigantic function of below the constants. Yeah, let's put it below the constants. So we're gonna have let put list first. Let's do put list first. So put list, you're gonna receive an address. I also think we have a thing in there. We have a computer, which we should do the structuring on it. So let's get the H register out of it. Computer machine T, and you're gonna return a new machine T. And what are we gonna do? We're gonna do a set register. We're gonna do a set register. So set register with list. So what's this takes? This takes a register and a cell and a computer. So the cell is gonna be it's gonna be list a DDR. And which register we're gonna do it? We're gonna do it the one that is coming from the arguments. So actually this is wrong. This is a register, cell register. This is H register, and this is that. Here we go, right, Money? That's it.
Diref cell.
No. Put
Wait,
list.
put list.
Yeah.
Yeah, that's it.
Awesome. So now we're going to implement the get list, which is a little bit more complicated. So get list receives as an argument another register. We're also going to use the H register, but we're also going to need the store this time. So store. My first instinct is to use deref cell. What's your thoughts? What are your thoughts, May?
Yeah, that's what you should use because you need to look at whether it's a free variable or if it's a list or if it's something else, basically.
So we're gonna do deref cell get register computer. Yep. Compute store with, and then we do this. So these will return to us these things, right? Reference, list, and then other. Is that it? This returns a cell. Cool. So if we have a cell dot reference with something that we don't care, we're gonna do something about it. So something about it. If we have a list we're gonna do also something about it. And if you have a catch-all, we're gonna do computer with fail equals true, I believe. Right?
Right.
So in the case of the list, we need to put, we're gonna return a new computer, computer with, so s register is gonna be the value of a, it's gonna be the value of a. Mode is gonna be equal to read. I don't remember how we do this before. Mode equals, it's like this. Okay, so there's that, and that's it actually, and that's our new computer. In the case of the reference though, we need to do a lot more stuff. We need to put stuff into the heap. So let's make a list, which is gonna be um, heap put heap put. Okay. So this is gonna be cell. Actually, we can just call it like this. So this is gonna be list. No, but it should be cell in this case to not be ambiguous. And we're gonna need to put h register plus one in. Not happy about it. Oh, this is right. And then grab that. We need to put store heap put list. The address needs to be h register, and this actually needs to be a computer. So, oh, not actually a computer, a store. So you grab the thing, you grab the address, you grab the store, you return a new store. Where are we doing bind? We should be doing bind somewhere. Does bind takes a full computer? Yes, it does. So we're gonna have to do fun store bind needs to be a cell. With two cells, the computer comes at last. So there are two things, and then we're gonna do computer with store. Does bind cares about the H register and the mode? That's a good question. And the answer is it doesn't. So that means I can literally just put this down here. H register equals H register plus 1. Oops. And the mode is equal to write. And there we go. So what are we binding here? So bind. We need to bind two things. So Marinho, do you remember when we use bind with ADDR, which cell do we use it for? Because I kinda don't.
Uh, In this case, it would be the
Oh,
result of the
it's
deref,
this
no?
ADDR, right?
Yes, the result of the deref. You need to remember it.
Uh-huh. So this comes reference, and this comes another reference, like this, right?
Yeah, yeah.
So this takes 2 cells on a computer. Why are you mad? There's something wrong with the types. Heap puts returns a new store. Yeah, there's something wrong with the types. I don't remember. I don't see what. Let's ask the compiler. Syntax error. Ah, parentheses. That's it, right? Am I missing anything? Look here. So let's go step by step. Get list. You receive a register. Um, you receive a register. If it's a, and then you do a deref cell on it, right? If it's a list, we just return the computer, put in the value of the list cell to the S register and switch the mode to read mode. If it's a reference, we put into the heap using the H register as the address, a cell which is list H register plus 1, and then we do a bind with the result of that. And then we increment the H register and swap the mode to write mode. Everything else goes to fail equals true. I think that's it, right, Manny?
Hmm. Does it matter that you are bumping the address on the H register before the bind?
No, because bind doesn't use the H register.
Then it should be okay.
Okay. Let's do an FMT. Okay. That's actually an okay. Like this is not great, but completely fine. I have a thing though. We also need to update other functions considering that the list is now available, right?
Yeah, we do.
Yeah. What is these other functions here? Set void, the unify void. Oh, this is for single occurrence variable in non-argument positions. That's not possible, right?
Basically, of course it is.
But we only have variables in argument positions.
Uh, he's talking about argument positions with respect to the currently executing predicate, not the one you are going to call.
Ah, okay. Oh, but this is a separate optimization. We don't need to care about this to have lists, right?
No.
Okay. Um, so now let's go all the way to the bottom. Uh, and let's check which functions we're gonna actually have to change because of the introduction of lists. This was surprisingly easy, right? Now it's just a matter of parsing them properly.
Isn't there an instruction for the tail of the list, like the empty list?
An instruction for the tail of the list. Let's see. Actually, no, let's see. Let's finish reading this portion. Set void. Here it is. No, it's a unify constant on it.
Do we have that?
Of course, we have constants already.
Do we?
Of course. Let's reread the implementation. Yeah, we already have all of this.
Man, I don't remember that.
Okay, so look at my code here. Unify constant, set constant, get constant, put constant, get constants from different reference cell.
Oh,
We already have
okay.
integers, man. What do you mean? Um, okay, now let's jump a few pages to the implementations. I remember at least unification. The unify value definitely needs to take into account the lists. I remember that much, but that's all that I remember. So let's start from the beginning. The complete set. You don't care, you don't care, you don't care, you don't care, you don't you oh you of course you care, you are put list, right? You don't care, you don't care, you don't care, you don't care. You care but you are get list. You don't care, don't care, don't care, don't care, don't care. Unify variable doesn't care. Unify value calls unify, and I think unify cares, but let's continue. Don't care. We actually don't have this function, unify local value. This is probably an optimization. Um, don't care. Doesn't care. No. 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 None. Also none. No. 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 Oh, indexing instructions. We don't have that, actually. Jump to the instruction labeled respectively V, C, L, or S, depending on whether the dereference value of argument register A1 is a variable, a constant, a non-empty list, or a structure respectively. Where is this being used? Switch on term. I don't think we have that. Ever.
That's an optimization we didn't implement yet.
Switch on constant, switch on structure, neck cut, get level, cut, auxiliary operations. Only Unify cares about the thing being a list. That's kind of cool. No, no. Yeah, man. Only Unify cares about it. So let's implement for you. Let's go to Unify. So it's in here, right? Let's check. If T1 isn't a list, if T1 isn't a list, yeah, this if is kind of we have to remap it for the pattern matching here. And T2 is a list. If T2 is a list but T1 is not, that is just like we need to optimize this catch-all, right? Essentially.
What do you mean?
Exactly that. So we make another one that ignores the first, and the second is a list.
No, we need to make a case where both branches are lists.
Oh, if the T1 is on a list but T2 is, then we just fail. Then the catch-all can continue. So this can just be what you said. So it can be like list v1. Oh, I guess cell list v2, and then we do something about it. Okay, what should we do about it? We need to do a bunch of pushes of the PDL, essentially. Um, sure. So let's do it. So this is going to be computer. We don't need any of that. Computer with store. Let's get started. Store PDL push. Um, it's gonna be reference v1, right? Reference v1. Then we do the same with v2. Then v1 plus 1, and then v2 plus 2. Is that it? Marine?
Yeah, looks okay.
Very freaking easy. Okay, now it's just a matter of parsing it, right?
Question: did we optimize atoms in the heap?
I have no idea. Does that matter for lists?
It might, for the tail specifically.
Which optimization are you asking for atoms?
Uh, if we have an atom that is a functor with uh, 0 arguments, do we need to allocate space on the heap?
Um, oh, there is the example up there. So let's actually go back. Not that much. Yeah, but it mentions something about that, by the way. I remember. Stack variables. It's before all this. Get variable, rest allocation. It's before that, before. There we go. Here. Um, it starts here. Programming with linear lists being so privileged in Prolog, it makes sense to tailor the design for this specific structure. In particular, non-empty list functors need
No, no,
not
no.
to
But
be
that's
represented explicitly on the heap.
for the body of the list. I wanna know if we have optimized atoms to not take space on the heap or not.
How can we check that?
Can we push atoms using the constant instructions, like put constant and such?
Put constant. Let's go there. Put constant. Um, the constant is just an address. No, it's just a constant, which is just a number. We
Yeah,
don't.
then we don't.
Is that a good? That sounds like a good thing then.
No, it's a bad thing.
Wait. Could you explain to me again the problem? I don't think I got it.
Basically, we need to allocate a cell on the heap for atoms, even though they shouldn't take any space.
But a constant is only a number, not an atom.
Yes, because we haven't implemented this for atoms.
Oh yeah, there are no strings. Atoms are not literals ever.
No, 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 not strings. Atoms, as in functors with arity 0.
Oh, what you're saying is that we should treat functors with arity 0 as constants.
Yeah, there's an optimization for that in the book as well.
Yeah, but that's not important for now, right? We can do that later.
It is important because of the empty list.
But the empty list
Is an atom,
is an atom,
right?
but it is being treated as a yeah, as a constant.
Well, we won't be able to
We won't be able to.
because we haven't implemented atoms as constants in Karuta yet.
Ah, this is assuming that we have done that.
Yeah.
Okay, let's do it then. So how do we do that? That sounds like easy enough, no? It's just a matter of here we make this more options, and we say atom, and
Of
then off.
string, yeah.
We need to remember the name of the atom for the constant. We do. No, we do.
We do. Yeah, if you were doing this in an actual machine level implementation, like in C or assembly or whatever, the way you do is you would do this is you would intern the name of the atom to make sure that there's only one instance of it, and then you just remember the pointer, and you can have as many pointers as you want for the same atom, and they don't take up extra space. You see?
Yeah. So now we need to go to the parser. Well, not the parser, but the file where we define the yeah this thing. And there is a place where yes, so where we have the functor name and an identifier. We need to change this, right?
Uh,
Literal atom.
Yeah, instead of having arity 0, we need to use an atom
Constant.
constant, yeah.
So where are we doing that for numbers?
Although,
Although, I'm listening.
here, yeah, we should not do it here. We should do it in the. We have separate types for the for the data that we parse and the data that we actually use for the code generation, right?
I don't follow. What's the problem?
No, no, no. We have separate types for the data that the parser spits out and the data that the preprocessor spits out, right?
Sure.
It might be better to do this in the preprocessor actually.
Why?
Because then we don't have to actually add a new type to both layers. Well, not a new type, a new tag, I guess.
Wait, both layers? I'm confused. What are you talking about? Ah, you mean having to add a constant in here. I see. If we do it on the preprocessor level, we can just convert it on the representation, on the one that I just changed. If we do on the parser, we have to add that change here as well.
Um, Parser clause is a decal or a query.
Yeah, this is how we're doing for the constants in the case of numbers. We have them twice. We have them in here, and we have them in a machine as well, in here. Your proposal is to not do the atoms on the other level, because
It's
then the
not about.
preprocessor can
No,
do
no, no,
the...
no, 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 no. It's not about the machine. It's about the. Because we have the parser that takes the source code and turns it into a structure that we then run through the preprocessor to change a few things, and then we feed the output of that into the actual code generation, right?
Yeah, I'm still trying to understand the problem, because you said that you have to double up the definition. Is that what you're talking about? Or am I confused?
Declaration is a multi-declaration. Wait, no.
No, I'm talking about
Yeah,
this
parser.
is the
Yeah,
place.
parser clause is just a decal. Where is the definition of decal?
Here.
Okay, so the head is a functor, the body is a list of functors.
And the list of functors is there's an element which is the list of expressions.
Mm, yeah, if we do it at the
Here,
level of the yeah, the level of the parser, we will need to implement constants up there as well in the expert
So
too.
I am understanding things correctly. So your proposal is for us to keep it as a functor, and then in the preprocessor, we grab the functors with arity 0 and convert them to constants.
Yeah, and if you want to be extra type safe, you can change the functor in the expert type to not be a func, but instead, actually it needs to be a func. Hmm, that's kind of sad actually.
Let's go to the preprocessor and add this conversion. Um, remove comments. So we're gonna have another thing. Filter map. I already forgot. So what this does? Of course. Okay, we're gonna do a list map.
Actually, there is another way of doing it, although that would complicate the code generation. Let's not do that.
Hello, Magetta. Did you just have dinner?
No, actually, I still didn't. I just my parents wanted something.
Sure. So we want to functor to atom, right, Mario? Functor to atom.
Yeah, functor to atom, something like that.
Let's not here do that. Functor to atom. We're gonna receive a clause, which is a parser clause, AST parser clause, and we're gonna return um, actually that's a good point. What are you gonna return from this actually?
Hmm.
Can we do it on the level of the preprocessor? Because the preprocessor only deals with clauses. We are talking about memory. Huh. So can we
Mm,
do that, Marinho?
actually, maybe not. Hmm. Where is the best place to put this?
I'm starting to think it's the code generation.
Hmm. Yeah, you're probably right, actually.
Yeah,
Now that I think
preprocessor is
about
only on the
it.
level of clauses. That's very sad. We're gonna have to touch it. Okay. Okay.
Should I try to make this variadic or just two relations at a time?
Wait, repeat the question.
Should I try to make sums to be variadic or just two at a time?
For now, just two at a time to keep it simple. We're gonna introduce variadics
Probably
about
best.
for lists, for example, for ranges later as well.
But if we have something for two, we can just nest all of them, right? So that should be fine.
Sure.
Uh,
That's gonna be. Oh man, that's gonna be so boring.
welcome to my life. I've
Marinho.
been implementing authentication for a week today.
Marinho,
What? What?
I have a question for you. So in which place are we gonna do this transformation exactly? I'm starting to think it's
Uh,
in here. Like everywhere we have integer, we just do a OR pattern with the functor with 0 elements, and then we just follow the same thing. What do you say?
yeah.
Okay, so in here, but it is not that easy though.
Yeah, it's not quite because we need to extract the name of the functor and then the cell we build is different.
Yeah, this cell is completely different. Okay, so how can we do that very easily? Well, my first instinct is to make this a function. Yeah, I think that's gonna have to do it. So put constant we're gonna receive the three things, and then we end the cell, of course, constant, and then we just put this in here, and then we replace this with this. There we go. So if we have an integer, we're gonna do put constant generator store allocator, and we're gonna do cell integer int. If we have a functor, so this is a func. Um, yeah. So we're gonna have functor func. We have elements, right? So we're gonna have elements in here, and then when length. How do you grab the length of the list? Is it like this? Something like that. So what's the problem? These expressions should not be a constructor. The expected type is blah blah blah. What do you mean? What do you mean? Oh, it's swap it. Okay. Marinho, is it like this? Cell atom doesn't exist. I wonder. Yeah, this is just LSP going nuts. And then we should also grab the atom from there, right? So the name f, and then we say name f equals atom, right?
Uh, yeah, right.
Is it like this? Or how do we rename this thing? Actually, I'm just gonna grab the name f. Name f. I think it's like this. Yep. Oh, wait, this is not what we care about. We care about the arity, right? The arity being 0 is what defines an atom.
Technically, the arity should always equal the length of the list of elements.
Is this assured at this point? I think it is, right?
It is, if the data came from the parser, yes.
Okay. So now let's go to the other places where we have integer, and also, yeah, we're gonna have to do a very similar thing. I think you should make this function like global. Global for in the context of having multiple things. So let's put it in here. And ooh, but this is missing the wait. Where is the const? Oh, the const is coming here. Mm. Okay, so const function. There you go. So this. Now let's actually go back. Let's put this outside here. we don't need the let in, and this can go back to being a let. And we put const here. Okay, now we should be able to, yeah, here, same thing, same freaking thing. So actually I'm gonna copy this one. Integer, there we go. So there we go. And we're also gonna copy that. Okay. What else? Same thing in there.
Okay, now I'm gonna go have dinner. Perfect.
Sure. Ooh, but this is different. This is actually different. Put constant. Yeah. This is asking for a tuple. Uh, Asking for a tuple. Like so. Are we gonna do the same with atoms in this case, Marinho?
Yes, why not?
I don't remember. What is the arg register doing here?
It's the register where you're putting the constant.
So it's gonna be the same. So we just put arg register. And then all of this can be nuked. Integer. Is this the last one? Yes, this is the last one. So let's grab this. Integer. So let's see how we can convert these ones. This is the same with the counter plus 1 at the end. Um, the thingy is actually this. And the other thingy is cell x counter. And then we should do exactly the same. Yeah. So x counter. And then we do put constant. And that should be it, I think. Yeah. And then we can.
Man, why do people make giant PRs? They're a pain to review.
Yeah, they are. Oh, this is also missing the counter plus 1. I need to put an extra parenthesis in here. Let's see if this compiles. I'm having second thoughts. It doesn't. So 292, put constant. So what am I doing wrong? You see any problems in there?
Cell.putConstant is not a function.
That is true. I need to put the fucking uh, um, extension for that. And then in here, I will fix that later. Actually, I'm gonna put even a to do. Um, fix this with ppx for constructors as functions. Does this compile? It does. Okay. Did we do it? Now we have full-blown atoms as constants. Is this enough? Can you go to the parser now?
We also have to deal with the places where we do gets and unifies, no?
Gets and unifies. Let's go there. You mean like the place that we do integer in here? Plus.
No, like, don't we have also get constant and unify constant or something?
Yes.
Yeah, we need to handle.
I don't think they are exclusive for integers right now. They are generic for any constant. Let's check. Get constant. There we go. So there it is. This is not specific for numbers.
Yeah, not in the evaluator, in the code gen.
Code gen.
Because if we try to do a get on a functor that has 0 elements, we should do a get constant instead, no?
But that's exactly what I just changed. No? I just did that.
Uh,
Look. Get constant is the const.
well,
If you
well,
have
in
a
that
functor with
case,
30
well, in that
0,
case, well, in that case, the function put constant has a terrible name.
no, yeah, okay, so we can change the name. Which name do you prefer for these 3 lines?
Um, what about, I don't know, add constant instead of put constant?
Sure.
That because that's more similar to add instruction and there's no risk of confusion.
Put constant, add constant. There. There. Parser time? What else?
Okay, we are handling constants for atoms. Unification should already work because we don't care about integers specifically. Yeah, I think that's it for now.
Okay, so
Parser time.
parser time. So let's make an example. Lists. Karuta. What type of example would you like to make, Marinho?
Uh,
I kind of wanna
well,
try doing an add, like it's essentially a zip with an addition for lists. What do you think? So you
zip
do add,
with addition.
yeah. So you do like, and then in here you do 1 2, and this you can do 3 4, and then the output will be 4
That's not how you
4.
write lists, by the way.
That's how it's written in here.
No, no, no. The pipe is how you build a console.
Oh, it's comma. This.
Yeah.
So it's gonna the output that I'm expecting is out equals 4 6. What do you think? Can we do that?
Yeah. That makes sense.
We're gonna assume that they have the same length for now. Okay, so this is what you said about the cons is in here, right? I do something like
Yeah, it is.
head. We're gonna have to introduce. Okay, that's parser complication. Well, let's actually write the base case first. So the base case is the empty list for both, right? That's an empty
It's
case.
empty list. It's empty list on all three actually.
Empty list on all three. No, it's not empty list on the output, right? Because when these are empty, when the first two are empty, the third one is not empty.
Why not?
What? We are constructing the list, the out list, based on the destructuring of the other two.
Yes, if you have two empty lists and you are adding them together, the output should be an empty list, no?
Oh, okay, that's true. I was kind of referring to this though. So h1, tail 1, and then this is gonna be h2, tail 2, and these will actually have multiple things. So the first thing is that we have to do a plus on it. So we're gonna have h1, h2, hr for result, and then this is gonna be add again, but now passing tail 1, tail 2, and let's this is gonna be hr out or something like that. And if you have something in here, this is just holds. Is it something like this, or am I dreaming?
Yeah, that's not it, Lemos.
That's not it. Okay,
Yeah, you need to do something.
where am I getting
You
wrong?
need, okay, you need to actually destructure the out on the argument as well,
Reason?
because we're assuming the two input lists are the same length, right?
Yes, sure.
Which means the output also needs to be the same length, right?
Sure.
So it makes no sense to destructure the two inputs but not the output in the argument.
I don't follow at all. Let me try to. Yeah, I don't follow at all. These we need to destruct because we need to get the heads out of them, right? This one we don't have to
And
do
we,
anything about that.
actually we do. We need to get the head as well.
Why?
Because that's the output variable for the plus.
Oh, you mean this? Tail out.
Yeah. And then the tail call is with tail out, not hr out.
I see, like this.
Yeah.
Yeah, but I have a
And
question.
you can get rid of line 2.
That's true. I have another question. Don't we have to start like? How is going to figure out that these can be? Oh, but this is a variable. This binds to anything. But this I'm going to hold on this one because these are not empty. This one, this is a variable, so it can be this anyway.
Beautiful. And it's even tail recursive.
Okay, but now I have another question for you. So, how are we gonna do this destructuring thing? Is this like we're gonna do like a functor thing?
That's just a normal get list, no?
No, okay. Let's go back because I think there's some confusion. I remember last time that we discussed about lists, you asked me if you're gonna do lists as a syntax sugar for functors, right?
That's in terms of semantics, specifically about Declarative semantics. That has no bearing on the runtime representation of the list.
I am more confused than before. So are we gonna create a new thing in the AST just for this?
Uh, we could, but we probably shouldn't.
What are we gonna do then?
We agreed that we would use the functor with the empty name for the for the list cell, with arity 0 for the empty list and arity 2 for the pair, right?
Yeah.
That means we need to special case those two functors when we generate the code to emit the list instructions
So
instead.
they are functors under the hood. I was not dreaming. This is just a misleading syntax because those are just ugly functors.
Yeah.
Okay, so I was right. Okay, I'm understanding things. I'm understanding things. Okay, so where do we do this hack that you just said? Do we do that in the parser level, or do you want to do it somewhere else?
We should do it in the code generation. In the parser level, we can just emit functors with the empty name, arity2 and arity0, right?
Mm-hmm, mm-hmm, mm-hmm.
And then in the code generation, we special case those two functors to use the list instructions instead of the normal functor instructions.
Yeah. Okay, so let's start by checking our tokens, I guess. So Lexer, do we have open close brackets? We do. Left delim and right delim. We're gonna use those. So if we go to the parser now, which is in here, this is where we need to do something about it, right? This will be an expression, I believe, right?
Mm, yeah, it will be.
Okay. So let's first treat the um, I don't know. Where are we gonna put this? This is not a functor. This is not a maybe functor. This is not a declaration. This is not a query. This is related to the somehow, like this is close to a list of identifiers in a way. Um, so it's gonna be an expression, right? So we're gonna do like I don't know, left the limb, um, and then we have I don't know XPRs, which is a separated non-empty list, comma, and then expression,
Why does it have to be non-empty?
because the empty case is going to be a special case for that was planning to write later. Um, and then I don't know, write the limb. Something like that? Or am I far from it?
That could work, but can't you just reuse the list identifiers here?
Can I just reuse the list identifiers? Where is list identifiers being used? List identifiers. So I'm using this in only for functors. Do you want to use them in here? That's what you're saying.
Yeah.
Okay, so how are we using them in here? So something like this. But we're not gonna have an identifier first. We just have left it the limb, expressions, list identifiers, and then we do functor name is empty functor. this is expressions.
It's not quite that, because we actually need to. We have a list in this case of expressions, right? As the result of parsing, we need to turn it into a chained list. Basically, we need to turn the first element into a pair, a functor of arity 2, right?
Ah, you want to like nest them together with a bunch of functors inside,
Yeah, well, I think
like a
we're gonna need to
fold,
do a fold here, yeah.
like a fold. Let's do the fold. So list fold left. The initial thing is gonna be empty list. Is this how you do empty list in OCaml? I keep forgetting. Expressions.
Actually, that's not quite right either, because the way you're doing it, you're still going to. Hmm.
Still going to?
Yeah, the thing around the fold is going to be like. You're gonna have to get rid of it, actually, I think.
I don't get it. Could you elaborate?
Because like the way you're doing it here, um, you're going to make a functor of arity 2, which is actually a fake arity because the expressions can be any length, right?
That's no. But it's arity true because we're gonna grab the remaining, like we're gonna grab the elements that we just parsed, and you're gonna put them nested inside the elements, and we're gonna do that for all of them. So they're always gonna be arity true.
Well, in that case, the construction of this functor should be inside of the fold, no?
Actually, yeah. I think it's better to write them upside, like revert the thing. We first fold it, and then we create the functor. So it's gonna be like this, and this thing is a part of the folding function, like this. But then the problem is that this now we have okay, so that's another problem. What's gonna be the final? This is gonna be a list then.
No, actually.
What that this is gonna be?
The base, like the initial value for the fold, which is actually going to be. Oh, this needs to be a fold, right? I think.
Sure. What's gonna be the initial accumulator?
The empty list. The
So
functor
this
with no name and arity 0 and no elements.
oh, so this is a functor. Let me grab a functor. So what you're saying is that the initial accumulator is this guy. There.
Yeah, and the functor name is the empty string.
And the arity of it? True.
No, 0. It's empty.
Oh, this is what we're gonna do folding upon. I see. Why does it need to be a fold right?
Otherwise, you're going to build the list backwards.
Otherwise, we're gonna build the thing backwards. I don't follow. Let's write this in the code here. So let's imagine that you have. Let's pick this list here. So one shoe. What are we gonna convert this to? This, right? This, and then this, that. No?
Yeah.
So this is always arity true.
Yeah, except for the last one.
And it's why we have to do from the right.
Because
Oh,
otherwise, you're
because you
going
want
to
to.
build
Oh,
the list backwards.
oh, it's because our initial accumulator is the last. Is the last one. That's why.
Yeah.
I see. So cool. So let's do that. Let's actually keep this around here. Okay, so what are we gonna do in the fold? Man, I don't remember the syntax fold. It's just a
Dude,
normal.
you're literally doing fold right, cons, elements, empty list. Except the elements and the empty list, they have a funny representation.
Sure. Fold right, OCaml.
Concats. That solves all the problems.
uh, oops. Okay, so it's the accumulator first. It's no. Ah, list module OCaml. I just want to know the order. Fold right. The element first. Cool. So this is an element. This is the ACC. And what are we gonna return, Marinho? We're gonna return
A functor with arity 2.
arity true. I have it. And then it's
And
just
we
a
are going
const
we're just going to build a list with the
element const
accumulator.
ACC.
No, you're not consting the element. It's a list with the element and the accumulator.
It's a list with the element in the accumulator. What? No. That doesn't make sense to me. Let's backtrack. The element is gonna be true in this case, right? We're doing a fold right, and the initial accumulator is this guy.
Yeah.
Cool. We need to create this list, right, for the elements of this other functor.
We don't because well, yeah, we have to build the list with the head and the tail basically.
Exactly. So the head is the true,
Yeah.
and the tail is the accumulator.
Yeah.
What is wrong?
So you just put them together in a list. You don't const the elements onto the accumulator. That's wrong because the accumulator is not actually a list. It's a functor.
Ah, I see. You're saying to do this. This, Camo, I guess.
I hate floats.
Welcome to the club, Magetta.
I mean, I will purge floats from this language. There will be no floats.
Anyway,
Welcome to the club, Magetta.
so yeah, is this what you mean, Marinho? This is wrong, and I'm misunderstanding something. The
Dude,
element is the true, and this is the accumulator. We just need to do a
dude,
cons.
the functor you are building is literally isomorphic to a cons cell.
That doesn't help me. Uh, what's okay? Let's backtrack more. This is the empty list, and this is the true. We are
It's not
folding to
it's
get
not the empty list, it's actually the functor that represents the empty list.
exactly. That's what I meant. Um, this well, but then okay, but this needs to be a func as well, right? And that's wrong.
But it is.
It is? Are you sure about that?
Well, actually, it can be any expression in the Karuta language, technically.
Yeah, but a func only accepts other funcs, right? Oh no, we changed that. We changed to be in a list of expressions. That's why. Okay, but this is still not what you want, right? I'm not getting what you want, Marie.
No, this is correct.
But this is putting in a list the first element and an ACC. Why can't we just do a cons?
Because the ACC is not actually a list at the OCaml level.
Ah, that's why. I see. Thank you. Is this it?
I'm not sure if that's the right syntax for a function, but otherwise, yeah.
You mean here?
Yeah, let element act, like, that's weird.
Well, but that's what what we've done multiple times, as far as I can tell. Like fold left, and then this, and this is a gigantic let. Fold left.
No, the point is, I'm not sure if that's how you write a lambda in OCaml.
Ah, no, it's not also. It's this. Better?
Yeah, now it makes sense.
Okay, so are we done with it? With parsing? Is this it? No, we still have to deal with this shit, right? We just managed to make this work. We have to make this work.
Yeah, we need to make a case for a list that has a pipe instead of a comma before the last element.
Pipe. Pipe. There we go. Wait, could you repeat what you just said? I think I missed it.
Yeah, we need to make a case, um, a syntactical case for something that is a list, but it has a pipe instead of a comma before the final element.
Isn't just copying these two here and replacing commas with pipes?
Hmm, not really, no.
Really? That's weird. Um, are you sure? This is the only place where we're doing this type of list manipulations. Everything else is just using them. For example, here it's using itself because it's recursive and it uses the expression in the middle. Are you sure? It isn't just a matter of like grab this and replace commas
Yeah,
with
we shouldn't
pipes?
do that because if you do, you're going to allow pipes as an argument to an arbitrary functor, which is nonsense.
That's not true because before the pipe needs to become an expression or an expression comment.
Which is also what's inside of the argument list for a functor.
Yeah, but what you said is that I would allow a pipe to be an argument for a functor. And
You're,
as far as I
I'm
can tell,
saying,
that's okay. Go on.
yeah, what I try to say, and maybe I expressed myself poorly, is that if you just change this clause of the syntax definition, you're basically saying, okay, you can put a pipe, a trailing pipe, before the last element of any argument list for any functor.
Ah, okay, that's wrong because this is only allowed in the head of the declaration. But wait, what you said is
No,
that a
no, no, no,
problem?
no, not the head of a declaration. It should only be allowed in an expression, actually.
This only needs to be allowed in an expression. Wait, let's go back to what you said before because in the beginning I said it was wrong, but now I'm having second thoughts. You said that if I put it in here, I will allow this to be an argument for any functor, right?
No, 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 no. I'm saying that you allow a pipe to be used as the argument in the argument list of a functor.
No. The pipe is not going to be the argument because it's mandatorily preceded by something else.
No, 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 not the argument. What I'm trying to say is if you just do what you're trying to do in the list identifier, you're going to allow something like this. Let me just write it out. It's probably easier. Add 1, 2, 3.
Let's go. Oh, you're
Yeah,
talking
you're going
about
to allow
the
this, which is nonsense.
because you're missing the surrounding brackets on that. I see. We are missing the surrounding brackets. Um. Okay. Okay, I see the problem. So it needs to be on a level of expressions, as you mentioned. It needs to. I have a question. Can we pass arguments to these definitions? Do you guys know?
I doubt it.
What?
Like, can I put
If
a
you can pass
separator in here
argument to what?
to this?
Oh, I don't think so.
Because it would be kind of nice, so I can send commas and pipes from down here. That would be awesome.
You need to do it on a rule, right? You're just defining branches of something that is meant to be used in a rule, something like that.
Okay, so Marin, we do left the limb here, right? And we're gonna end with another right the limb. Um, so this is already taking into account the empty case, right, Maria?
It is, yeah.
So I can just do the separated and blah blah blah.
Yeah.
So I put expression, oops, pipe, and we need to give this a name, expressions. And is that it? What do you think? Is it at least close?
That's not it. Pipe can only appear once.
Wait, you're not gonna do it like Erlang, allowing this to have like x2, this?
I don't think that's valid Erlang, is it?
In Erlang you can do that. At least I have the memory that you could.
Hmm. Yeah, no, I don't think you can actually. What you
Really,
can do,
Erlang
yeah,
only
what you
allows
can,
the head and the tail?
no, what you can do is put commas before the pipe at the end.
I was so sure. Wait, put commas. Oh, so to get more elements, you mandatorily needs the pipe only for the tail, but you can have more elements by using comma.
Yeah.
Okay, that's weird, but okay. Are we gonna do that right now? Like, are we gonna allow comma here? I don't think we should
Uh,
do that right now.
well, if we don't do it, then the rule that you need to implement is very easy.
Well, if we do it, does that complicate? I feel like that's complicating like the. Is that complicating anything? Actually, that's the thing.
Probably not.
Ooh, it worked.
Okay. So, but let's. Oof.
I mean, it's not as if the commas will let us represent something that we couldn't before.
Okay, so this is gonna be a comma, right? But then we're gonna have a pipe, and then we're gonna have
Another
another
expression.
expression, which should be like tail, and then we have the right the limb.
Yeah.
But then I have a question. We're gonna have to have another rule for the case where we don't have commas, like something like this.
Why?
Well, because this is a non-empty list.
And it must be non-empty. That is correct.
Oh, because this is already covering this case. That's what you mean.
Yeah, you can't have a pipe with nothing on the left of it. That's nonsense as well.
Okay. So this is it. We have expressions, which is essentially the head plus more stuff. If you like the more elements, or mandatorily a pipe, and then another expression, which is the tail, and then write the limb. Right?
Yeah.
What are we going to generate out of this guy? Is this another
Uh,
functor?
you're just going to do the same fold rights that you did below, but then you're going to use the tail as the base case.
The tail is the base case. Like this?
Yeah.
Okay, so now we can parse this and we can parse this, right?
Yeah, we should be able to.
Now we need to go to the code generation and make the special cases. So where are we going to do that? Everywhere that we have a functor?
Mm,
Like in here?
yeah, basically.
Mm. That's that's a little. That's gonna make the code ugly as fuck. We gotta think about this. Because you see what we're doing here? We are. Okay, let's write it first and I will complain later. So functor.
That's my lemos.
uh, is this how you do that, or is it the other way around? I keep forgetting.
Mm,
No,
that
this
should
is.
be it, I
No.
think.
Wait, it isn't. Doesn't need. This needs to be in a guard. Can I just do it like this?
Why wouldn't you be able to?
Okay. So if this is the case, this is a special case. That this is the least case.
Yeah, we need to check if the arity is 2 specifically as well.
Okay, so arity true, like this.
Yeah.
Okay. Um.
Run the formatter.
Okay. Wait. There's another thing we gotta do. We need to check if the token of the identifier is non-empty always. Where is the
The
ident?
token the
Here.
token of the identifier.
Yeah, because we need to forbid the user from putting empty in there. Remember? We need to not parse if he writes a functor with
Why
empty things.
not?
Because that's gonna fuck it up.
No, it's just another way to write the same thing.
No man, if he does like this, for example. If he does x, y. Whoops. Isn't this gonna fuck us over? Doesn't this?
Oh, you mean as a declaration at the top level?
Yeah.
Why would it?
Well, because it's gonna go on the case of a list, right? But this is not what he meant. This is just a fact. We talked about this before. That if we use the list as a syntax sugar for this, we should disallow empty named functors from the user space. We talked about it.
No, Lemos. There is a difference between a functor being used as an expression and a functor being used to name a fact, right? Or a predicate in general.
Sure. I'm still with the same question. If I write this, am I not gonna reach this case?
No, because this is handling the arguments of a predicate call.
Sure. So, what now?
Well, then you're calling a predicate with a list as the first argument.
Okay, so we're gonna allow the user to write in this way instead of this way for whatever reason.
Those are not the same, by the way.
No, no, no. I know that this list is not the same as this list. I know. I'm just pointing that this is the way that he should write a list, and we're gonna allow this to be written as well.
Well, if they are semantically the same thing, I don't see why not. Other than the fact that this looks kinda ugly.
To me, it's kind of the same rationale of the comment. If you write comment as a predicate name anywhere, we're gonna do something that if you want it to be real, like if you don't want it to be a comment macro, we're not gonna allow that, even if you try. I think we should do the same with lists. If you try to write this nonsense, we should not allow that.
That's not quite the same thing, though.
To me, it's the same rationale. There are a few things on the language level that we're not allowing the user to do because those are special treatment for the compiler.
Oh wait, so you're saying you're not going to allow the user to write the desugared version, is that it?
It's because I'm not seeing this as a desugar. I'm just seeing this as a hack for us to get it done faster.
It's not a hack, it's a desugaring the way that we're implementing it.
Yeah, but how can I say this?
We could implement lists as non-functors, but then that would complicate the semantics a little bit.
Exactly. That's exactly what I meant. We are using the desugaring strategy just for implementation's sake. We could not do it, but we are doing it because it's easier. If we are doing that, I feel that exposing this hack to the user, allowing him to write it like this, I wouldn't like it. But that's maybe my personal taste.
Well, if you can make that restriction and not complicate the parser too much, be my guest.
No, but isn't that just a matter of not allowing an identifier to be empty on the Lexer level? Like right now it can be empty because you're doing it like this, right? But if we manage to make it not like empty, and I don't know how yet to do that, we
Then
are
you're
done.
going to for yes, but then you're going to forbid also um, any functor with an empty tag.
Yeah, because empty functors are exclusive for lists.
No, but what about a functor with an empty tag with one argument? That's not a list.
Okay, that's gonna look ugly as fuck, but you want one? I should allow you to have one. Okay, okay, so we will allow this thing. Yeah, and not in making the true special case, that's gonna be a pain in the ass to make.
Wait, you guys are talking about syntax? I should get involved. Give me a sec.
Yeah, so if you take a
Let me
look
just do
here,
this formatter because it sucks. Oof.
wait, what?
Okay, I just ran the formatter and I changed the whole project.
Okay,
Um,
so what are we
okay.
talking about? We are talking about, okay, this is the program that we aim to be able to run today. Okay,
Mhm.
what is this doing? This is essentially zipping with these true lists using a plus. That's it.
Okay.
And then we were discussing, and we started this discussion last time. How are we gonna represent lists inside of the compiler? Marinho had a very neat idea, which is to just make lists syntax sugar for a particular function or functor of arity true, which is the empty functor.
Okay.
So when you write a list, the parser converts this syntax to this thing.
Okay.
And what we were
It's like
discussing is
just a
like,
it's
go on.
just a series of cons, right?
Exactly. We're using the functor mechanism as a cons, which is fine. But then we are now discussing if we should allow the user to write the list in that way as well, like literally treating as a
Oh.
syntax sugar.
Um. I mean, I think so, but you would have two rules, right, to do the same thing.
No, no, no. Those are not true rules. Like this program and the program that was before the query, they would be output exactly the same result,
Yes, the output is the same, but you need to match the and process the lexemes differently.
Which we're already doing.
which we're already doing.
That's the easy
So
part,
then,
actually.
That's the easy part.
yeah. So then,
Yeah, but I want, and what I was trying to propose to Marinho is that because like we are exploiting this particular functor to make the lists, I don't want I had the idea of not allowing the user to write it this way and not allowing this to parse. And then
hmm,
Marinho said, if you can make this exception in the parser not be too complicated, be my guest. And then I said, well, it's just a matter of going to the identifier and making it non-empty always. But then
yeah,
Marinho
I
said,
agree.
what if you have this functor? What now?
Well, then that is wrong.
No, then I would not allow this as well. But the question is, should we allow this type of shit?
Because this is not a list, it's just a normal
Yeah,
functor.
exactly. This is not a list anymore. This is just a functor that happens to have an empty name.
Yeah, I see.
So the question is, are we going to allow users to write functors with empty names in the language? That's kind of the question.
I That's probably a mistake, but just
Yeah,
block it.
yeah, that sounds like a mistake. But Marinho doesn't see a problem with it.
Well, I trust more Marinho than I trust myself, so
Yeah, I say the same. Uh, so we're gonna allow this we're gonna proceed with this, which makes our lives easier. So let's continue in the code generation here. Okay, so if we have a functor name that is empty and the arity is true, what we should do, Marinho? We should do something different than this, right? For sure.
Um, Scene registers instruction. Oh, this is for the arguments, right?
Yeah, this is for emit argument and kill nested if not including. What a name. So what's
Yeah,
gonna be the difference?
we need to do something basically kind of similar to what's being done on the normal case, but the instruction that we need to add is different. We need to add
What
the
about the
new
scene
list instruction.
registers?
What about the scene registers?
The
Well, we need
same?
to. Yeah, it's the same. Everything's the same. Just the instruction is different. And
That sucks.
yeah.
Okay, for now let's just copy paste because making a function, and this is using a lazy thing, making a function of this is going to be terrible, so let's just keep it as it is and just swap. Okay, so we like
Don't.
underscore
Yeah.
this, and then we do let instruction, and then we make a
Oh, but the instruction we need to use actually depends on the instruction we get up there.
really instruction. So you want to let instruction equals match. So what are the available options then?
I think, if I'm not mistaken.
It's variable or value. And those are parameters. We don't know which instruction can be. It can be any of them.
Ah, that's not great actually. Ah, and we can't even pattern match on them because the constructor functions kill me.
Wait, don't we have a particular like small set of instructions that we care about, and the catch-all is like whatever?
Well, in this particular case, I think it can either be a put structure or a get structure, and those we need to become a put list and get list.
Wait, it can be a put structure and what else?
Or a get structure.
Get. So put structure and get structure, right? Let's actually see this function being called. Okay, so we call it in here. And okay, so it's the variable and the value case. The variable is set variable or unify variable, and the value is set value and unify value. Are you sure?
Hmm.
Yeah, so it's only variable and value that we care about for the instruction.
Wait a second.
Yeah? Yeah, sets, unifies. Yeah, this is never going to be a put structure or a get structure, Marin, essentially. Essentially. Yep.
Oh, okay, this for the arguments of a functor, not for the arguments of a predicate call.
Yeah, seems to be the case.
Right, in that case it can be set or unify, right?
Yeah, it can be set variable or unify variable. For variable, and for value, set value and unify value.
Hmm. Well, it's not going to be a variable because we're only going to hit that case if we're dealing with um, an actual functor, right? Which is a constant. Well, in this case, it would be a uh, it would actually need to be. I think it would be a put structure followed by set value, or a get structure followed by a unify value.
Wait, so we only care about the value cases because again, there can't be in that instruction anything related to structure. Let me show you. So we only have variable and value that are available down here, as you can see. So value and variable, which are the ones that we are lazy forcing down here. So this instruction can only be a variable application on a value application. You said you're not going to have the variable in this case, so this must be the value, which are set value and set and unify value.
Scroll down a little bit, please. I want to take a look at this again. Let's see. We do the add instruction.
Yeah, let me go down to the original one. This is the original one.
We add the instruction, and then if we're in the query, we just say terms, otherwise we add the functor.
Yeah, to do using cons.
That would be for the contents of the list in this case.
Yeah, I agree.
Actually, I don't think we care about this case. In fact,
Oh, in the case of in this function, emit argument in queue nested if not in query. We can just treat them like whatever. Both are functors.
yeah, because here's the thing. The way it works is if you are entering a predicate call, um, and one of the arguments is matching a functor, we normally do a get structure, which would have to be replaced with
Get list.
get list. If we're in a query, or if we're preparing the arguments for a call,
Mhm.
we would use a put structure, which would become a put list.
Mhm.
But then, if you're trying to put a list as the argument either inside of another list or inside of a functor, you just use set value or unify value in that case, actually.
Okay, so we can just leverage what we already have.
Yeah.
Okay, but look, this is the next case. So if I do the grep for functor, this is where we were. But for, well, this is for atoms and this is for where we were. This is the next case. And this one we are doing a bunch more stuff, so maybe this is more interesting. So what is this? This is emit single queued argument. Do we care? That's kind of the question. Do we care about this one? This is calling at the end the function that we just were, by the way. But it is also doing all of this other stuff that I don't know if you care about or not.
We do, actually.
We do.
We do because this is where we actually build the functor. Or, to be more precise, where we emit the instructions that will construct the functor at runtime.
So we need to swap this, is that what you're saying? Because like this is applying the func to generate the instruction. And func can be put structure and get structure. So this is where you need to swap it for the list cases.
Yeah.
But there's
Yeah,
an
that
easy
is
hack
correct.
for this one. We add list there and we just say put list, which I don't remember if I didn't introduce those, I think. So let's go up here. Yeah. So what do we need to save for these things? So put list and get list, I think only require registers.
They only require the register, yeah.
Register, and we also have get list, which is also a register. Okay, what is the argument? A register. Awesome. So this is put list is just working, and then we do the same with the get list, right?
Right.
Then, in down here, we can just do a check before doing this instruction. We do an if nameF equals empty and arity equals true. Then um, list else func. What do you think? Is that enough? Marinho?
Yeah, it should be enough, but we're passing the name F and the arity there. Is that a problem? I don't think it is it?
Oh, I already have them in here.
No, no, no. I mean for the new function that you're calling list here.
For the new function that I'm calling list. What do you mean?
Yeah, those I think you may need to destructure the V and ignore the things that you're not gonna use.
No, the V is always a register. Oh, they are not always the register, actually. You are right, I need to destructure the V.
Ay, ay.
Go, Mageta, what do you want to show us?
I know, I'm just doing FFI now. I'm
Okay.
just sharing my screen so you guys can see what I'm doing if you want
Okay,
to.
so you mean like this, right, Marinho? Like this.
Yeah, basically.
Get rid of you, put it in there. Cool. Now, okay, this was very easy. We just swap the instruction. Everything else can keep the same, right?
Right.
Okay, so functor. Let's go from the beginning. This is where we were. We already discussed this one. This is for atoms. This is what we just discussed. This is for atoms. A new one. So what is this? This is emit. Same thing, right?
Hmm. Same thing, but we may need to. Hmm.
I think it's this, right? You put C. Yeah, if it's C++, you need to emit with a C block.
What is the exception, Marinho?
No, I'm just wondering if we have actually treated the empty list case in everywhere that we need to.
Well, we're gonna discover that pretty shortly. If nameF and arity equals true, then func, well, then list else func. And this is a nameF. I don't think so. And in here we're also doing the special scenario with query, right? Where we need to fold first or and then add the instruction later or vice versa. Can we keep that, Marinho? I think we can. Should be able to.
Yeah, we should be able to.
Okay, so that's progress. So functor. Let's start from the beginning. So this is atom. Yeah, right. This is atom. I already discussed this one. Atom. Already did. Atom. Just fixed. Atom. This one. Oops. It's yeah. This. So what is this? This is emit body. So this is emitting the body of something. Particularly emitting the arguments of something. The question is, do we care? We're doing a put value in here. Do we care about this one? This is not a put structure or a get structure. This is already doing put values.
I don't think so, no.
Yeah, I also don't think so. Yeah, okay. Previous p register. What is this?
This is so boring, Lemos.
Oh, this is cell.call. This is just for calls. Generate functor. raw register find. Is this a problem? This is doing a put structure here. That feels like a problem.
Yeah, we need to fix this as well.
So
Yeah.
if namef this
Why am I
and
typing
everything,
everything? I'm so dumb.
then and we
There we
also
go.
have the else. So what we're gonna do? We're gonna do a cell put list, right?
Yeah.
Put list. So put list, and this just requires the register. Everything else can be kept the same, right? I believe.
Um, I think in this case we may actually also want to handle the the constant case as well.
Oh, the constant case. So you mean like if the arity is 0, we do a put constant instead of a put structure.
Um,
Are you sure? I think we should actually.
yeah, I think we should.
Okay, so do we have else ifs in OCaml? If, else, OCaml. I
I
Just
don't
don't
do
think.
else and then if. Just nest it normally.
Yeah, I don't think it's compressed on the same word. In F sharp it is.
Okay, so else if
But why
arity.
Magetta? It's literally just a space.
Well,
Okay, so what is the things for put constant? It's a constant in a register. We need a constant though. So what's gonna be the constant?
It's the
Our
atom with the name of the functor.
the atom
and
with the name of the
documentation
functor.
makes the code so hard to read.
Like this, right?
Yeah.
I, ne- I think we should remove all the documentation. Oh, never mind. It's something I would say, right?
Yeah, that's definitely something you would say.
Man, I'm making an effort because I need to, right?
This is
But
it.
I
This is all the cases of functors, Marin. Do you want to see if it works? How badly you think it's gonna fail?
We need to implement printing for lists as well. Otherwise, I mean, technically they should be printing already, but they're going to print as the desugared functors.
Which is gonna be terrible. So let's fix that first.
And I don't think we support printing functors with the quoted names when they have special characters. So there's that.
Yeah, one thing at a time. So uh, the register is a cell T. So this is where we're gonna we're gonna check if there's a list here, right? So cell list, and then there's an address in here. Um, isn't this the
if
case where we just print an open bracket and then we call ourselves recursively or whatever? Marinho?
Mm,
It must be, you know?
yeah, that should. Yeah, that should work.
Where are we printing those things?
What do you mean?
Where? Oh, this returns a string.
Yeah, this just returns a string. We do the printing elsewhere.
Okay, so this is just this. Um, man, that's hard. Okay, we have a problem
yes.
because oh, this is already taking care of it. This is already taking care. So we just do open bracket and then inspect. We create a structure. Well, we pass the store and then we pass the structure with the new address to follow up. Is that it? Marinho?
Inspect the store with a new address to follow up. That should be a reference, not a structure, by the way.
Okay. Do we need to close this thing? I think we need to.
We do. We then need to do. We need to check if the point at address +1 is empty or not. Actually,
Wait. So you're saying
Should
let's
be
put this in a
the-
let's put this in a match. So
Oh.
we do let middle equals match this with um, and then we check. Wait, no. What you asked is just a store get, right? I'm dreaming. This is not correct. This can be there. And then we need to do store get store address +1, right? And if it is empty, then we
actually,
do
we should use a deref cell. In fact,
the ref cell. Where?
instead of doing the store get.
Instead of doing the store get, we do a deref cell. Okay, evaluator.
Actually, I'm not sure
Deref.
if we should do this in line because this is gonna be recursive.
Which portion?
The portion where we print the tail.
Wait. The portion where we print the tail. What do you mean? What do you mean?
Like, if the second element of the list, which is the tail, is another list, then we need to print a comma, the element on the left, and then we need to recursively check if the tail of that list is also another list or not, right?
Wait, so we're not gonna call this recursively at all, right? We don't need
We
this.
are
We don't need
for
this
we are
inspect here.
we're gonna call inspect to actually print the element on the left. We're gonna do that, but not for the tail call, for the tail of the list.
Okay. Okay, I'm confused. Let me just try continue. I will try to get along during the implementation here. So we're gonna keep this because this is for the current piece of list, right?
Yes, we're gonna print that.
We're gonna print that. So that's gonna be in the middle here. Actually, let's call this first. First. Then we need to do the same, but for address +1.
Yeah.
Address +1. If it's empty, we just yeah.
If
So
it's
tail. If it's
yeah,
empty,
if
we
it's
just return this.
no, not if it's empty, as in that empty, but rather if it's the constant, which is the empty list, which is the one that has, which is an atom with the empty name.
Okay, so you're saying this, right?
Yeah.
Okay, if it's not that, what else could it be? It can be a functor, right?
It can be another kind of cell, which
Well,
can be literally any.
yeah, but the cells that we care about are very they're like to me
No, no,
this
no.
one.
But if it's literally anything else, we need to print a pipe, then inspect the value, and then print the close square
Wait,
brackets.
print a pipe. We should print a comma.
No, because if this is the tail, but the tail is not a proper list, then we need to do that. And then we
What?
need to put a case. Okay, we have three cases, Lemos. We have the atom case for the empty list specifically, right?
Mm-hmm.
We have the case where we have either a reference to a list or a list directly, which means we need to do a deref cell in that case, right?
Wait, let's
Uh,
no wait. Reference address. Well, next address Or we have another list, you said, right? So next address here as well. We have this case.
Yeah, the problem is that if it's a reference, we need to deref cell on it.
And the same case for the list, right?
Um, oh, actually, no. If it's a reference, that's a free variable. We can just let that fall through, actually. Never mind.
Okay, so it's just this case. Oops.
Yeah, if it's a list with a next address, then we print the... We have to loop here because we need to print a comma and a space, and then we need to do the
The tail call.
yeah, but it's the tail call only for this branch of the pattern matching, actually.
Okay.
Yeah, that's not quite right actually, because that's gonna print an extra open bracket.
That's gonna print an next open bracket. Oh, we will see, we will see. Let's just continue for now. I don't know if this is gonna stay here anyway. Let's continue. So what else?
And if it's well, if it's anything else, then we print a pipe, then we inspect the store with that anything else.
Oh. Others. We print a pipe. Oops. And we concat that with others.
And then we concat that with a close. Oh, that's already down there. Okay.
No. I want to remove the open there. So this is close. You said.
Yeah.
Don't do we need this? Because I think this is the base case.
That's the base case, yeah.
So why do we need this? Or the close here?
Because that's the other base case.
Wait,
There are
what?
two base cases, Lemos.
Wait, a list always has to terminate with an empty list, no?
Not if you use a pipe and you put something else in the tail. It can be an improper list because dynamic types.
Ah, that's why I'm so confused with the pipe. Because this can be an improper list. Okay, this makes way more sense now. And then we... Okay, what about... Okay, now we have the problem with the open brackets. Now we have the fucking problem with the open brackets.
Yeah, if you want to hear what I would do, I would actually make another helper function just to handle the list case. And call that inside of line 6 instead of leaving it in line, because then you can tail call the helper function instead of inspect.
Okay. Let's rec inspect list. And this takes the store.
And you can take an address because we assume that the address is for
And string. And then we can literally grab all of this. Oops. And paste it in there. And then here we just inspect list address. And this needs
forget
to
the
be
store.
an store. Okay, cool. Okay, so what's gonna be the difference now? So we don't need to call inspect. Which of these cases we should call ourselves instead of calling inspect?
Well, first of all, let's put the...
This is the case. Inspect. Yes.
Yeah, you can get rid of the reference there because, well, this is a
Yes,
list.
of course.
But then to fix the problem with the open brackets, we just move that outside of the inspect list and put it in line 16.
So we put always here. And then this is just first plus tail, which I'm gonna rename it to head. Is that it?
Okay, and then the tail, we do a deref cell. I think that needs to be a cell.atom. Actually, no.
No, this is just LSP going insane, but I can put a cell here.
no, it needs to be a cell.constant with a cell.atom inside of it. Yeah.
You are right. Cell constant. Oops. What do you think?
Um. Yeah, just to make this look a bit nicer, put spaces around the pipe on line 9, and this should be good.
No, only on the right, right? S comma. Or do you want
Mm,
spaces here as well?
yeah, it needs to be there needs to be a space before as well.
Okay. Okay, so I think we have everything ready to fail miserably at trying to run it. So let's go. So we do lists, and we do an fmt, and do an exec Karuta. Let's fail. That's understandable. That should not be that.
Double quotes.
Yeah.
I hate nicks sometimes, man. To clone the project inside of the other. That's just awful.
Oh,
I'll do
I see the
that.
problem. Yeah, this expression should not be a function. The type is func, line 80. So this is a function somehow. Oh, I think it's
Oh, it's
because
because
they're
of the.
missing parentheses here. And probably the same applies here.
Yeah, it's because of the type annotation, right?
This expression has type AST func, but an expression is expected of type AST expression on line 80.
Right, we need to wrap those with a tag.
Um, we need to wrap those with a tag. Oh, the tag functor. Like in here. Right?
Yeah.
Wait, no. Actually. It's outside. Right? Needs to be outside.
Hmm.
And this probably is EST. Yeah, because the result of the fold is going to be a func. If you have a func and you wrap it with the tag functor, you have an expression. Right?
You also need to put funcs around the around the well, not just funcs, not functors actually. Huh.
Wait a moment, man. Yeah,
Yeah, I need to
here.
put a func
You're doing it in here. Should put a functor where?
around the line 81, the base case.
Ah. No, we don't. That's kind of the thing. Because this is a
No,
all of this is a func. All of this is a func. Agree?
but the func contains expressions, Lemos.
The func contains expressions, which are other funcs. Oh, you mean here, right? In here. Where do you mean, Marin?
Okay, the base case needs to be a functor, and then whenever we call the function in the fold, we also need to put a functor on that, an AST.functor.
Okay, so what you're saying is that I need to put a functor here, and you're also saying that I need a functor here.
Yeah, and you can remove the functor that's around the fold.
We can remove the functor that is around the fold. What about this other case up here? Same thing?
Same thing, but I don't think you actually need. Yeah, you shouldn't need the functor around the tail because that's already an expression.
We don't need this. Uh, so here and remove this. Like this. And same thing up here. So we don't need this.
Yeah. Also get rid of the type annotation on line 81.
81, that makes sense. Okay, is that it?
I think so.
Nope. The functor AST functor expects one argument, but here is applied, but he is applied here to 0 arguments, line 80. So here,
Functor is not a function, Lemos.
oh, but then it's just a matter of removing this.
Yeah.
81. The constructor AST functor belongs to the variant type list AST expression. Lib AST expression, lib AST expression, but a constructor was expected belonging to the variant type list. What? Line 81. So here. I'm confused. Is he talking about this list?
I don't think so.
No, but line 81. What else could it be?
Maybe get rid of the parentheses around the curly braces. I don't think that's it though.
No. Is this how you do empty list? It is, right?
I think so, yeah.
What is wrong with line 81? Am I blind? What am I missing here?
Uh,
The constructor AST functor belongs to the variant type, which is a useless error message, like what is this adding to me? But a constructor is expected belonging to the variant type list. What are you talking about? Can somebody help me here? What is it talking about?
What is it? Let me see.
It's saying that line 81, the constructor AST
functor.
functor belongs to the variant type, whatever. But a constructor is expected belonging to the variant type list. What is it talking about?
Functor. Can you show me the definition of this functor?
Ah, I know the problem. I will show the definition as well. So, functor is a tag with this record, right?
And that
And
is
and then these
okay. That is
elements
just
is a list
record.
of expressions, which are more functors, right?
Mm-hmm.
The problem, Marim, is that the ACC is being treated as a func, but it is not a func. It's already a functor. So this is wrong. This should not
but
be like this. It should be like this.
but Lemos, a functor has expression inside of it, no?
A functor has expressions inside of it.
Yeah, in
Yes.
particular, not just an ASC.functor, but actually a func. The elements is a list of expression.
Okay, Mageta, the problem is this is the functor. It has a record inside there, which has this structure. Elements is a list of expressions, which is recursive, as you can see. And then it's saying this nonsensical error message.
which I can't even decipher what it says.
The constructor AST functor belongs to the variant type expression. We agree. But a constructor was expected belonging to the variant type list. Variant type list. What are we smoking here?
Oh, wait. Isn't it expecting on the right of this fold? No, that's a fold.
Oh, we can check the fold.
No, but that is. Oh, wait.
Wait!
That is the neat, right?
No, no,
Yeah.
no, 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 no. It's okay. This is the problem.
Yeah.
The accumulator
Wait,
comes at
what?
the end. This is not Haskell.
That's a very silly order of the arguments.
Forget about composition, man. They don't have that here. You
Lib
actually don't even
parser.
have composition, the function.
Okay, so something is very wrong in here, folks. So now it's literally, well, I disabled the errors and I don't even remember how to re-enable them. And that's kind of sad. So how do I re-enable? There was a way to re-enable the warnings and I forgot. Because of course. Okay, so there's something wrong with the parser. We don't know what it is, but there is something wrong with the parser. Exception lib parser main here basics error. So how do we re-enable main here warnings OCaml? So how do we re-enable the warnings?
That's something I never do.
No, no, no. It was enabled at some point. I disabled it. I just don't remember how to re-enable it. Okay. There is a way to discover though. There is a way to discover. Let's first check the Dune file. No, this Dune file definitely not. It's probably this Dune file. Yeah, 2 months ago. Let's see the commit history. Some fixes. So what did I change in the file? Nothing of value. L3. What did I change? Aha! Found it. So it's inside the Dune file. And then in here, you put flags trace. There we go. So it's breaking on look ahead token is now integer, reducing production expression upper ident, and then it goes to state 25, initiating error handling, and then it just fails. So we have to backtrack this entire shit. Oh, but for this we don't need a full example. For this we don't need a full example. So what we can do is quite literally parse this little by little. Okay, so this parses, apparently. I wonder if this is gonna parse. Okay, so this is the problem is in here. I'm gonna suspect that the problem is in there. Yep. I'm gonna suspect even further that we can probably make this fail. Yeah.
I think
Yeah.
we're not splitting on the pipe. Try putting spaces around the pipes.
You mean here?
Yeah.
No.
Actually, now that I think of it.
No, it's not that.
Oh, it's
Okay.
Okay, so it's literally this. This is wrong, and this is the statement. This is the parser saying. So it's finding an identifier, then it's finding a left delimiter, up identifier, and then there's an integer. Look ahead is now on integer, but oh, the one. Okay, that was not it. But it changed the parsing. We cannot have numbers in identifiers.
Oh wait, it went further this time, Lemos. It
Yeah,
saw the pipe.
it went further, but this means that we cannot have numbers in identifiers, folks. Is that a problem? I feel like it is. Yeah. An
Oh yeah, we
identifier is
just
only
don't.
letters.
Yeah, we don't have numbers in identifiers.
Should we allow that?
I don't see why not, although it may introduce some ambiguity potentially.
But isn't a matter of like you, the only case that the numbers can be numbers if they are surrounded by things that are not identifier related, right? So delimiters and brackets and pipes.
Well, I suppose it's not ambiguous if we don't allow them to start with a digit
Yeah, pretty much.
or a dash, which we don't, right?
Yeah, so this is just a matter of putting digit here, right?
Yeah. And down there on the upper ident as well.
Yeah. Okay. So now let's put. Okay, let's take a screenshot. So this is going further on the pipe now, and it's going to the non-separated list. If I add the one back, oh, it actually parses now. It actually goes
Nice.
further. Okay. So if that's the case, let's oops. Let's uncomment the program like so. So now we should have a better understanding. Okay. Okay, we can remove the trace. This time I'm not going to remove it, I'm just going to comment. So, there we go. And we have a problem on line 700 on the evaluator, so 700. So what are we missing there? Evolve step. Oh, we need to put the get list and the put list. Of course. That makes total sense. Let's put it close to the put structure and get structures. Um, list. But this is wrong because this only takes a register. And then we do get list. Boom, boom. There we go. And this also does that. And we don't need that. Okay, maybe this requires more stuff. No, not put structure, put list. Okay. Unreachable. Dref cell. I think I know what it is. We are reaching a list cell in here, Marin. Should we put it in the 104?
We should put it in 104, yeah.
Dudes! Dudes!
It works.
It works!
Okay, that's cool.
Okay, but let's try to break it. So what other interesting programs can we add in here?
Append is nice.
Ooh, nice.
Have you ever written append in a logic language, Lemos?
No, actually no. I never done most of my of normal things in a logic language.
Hello, Vinicius.
Hello, Vinicius. I have a question. What happens if we do it this?
That's gonna break.
It's gonna break.
Because the lists are different lengths, which means 2 is not gonna match at some point, but then 1 is not gonna match either because not all lists are empty.
Okay, so what happens if we put X in here?
What happens if we put X?
What do you think?
I think plus is not going to generate a random number, so it's just gonna block.
And it's gonna blow up. Blow up.
It's gonna blow up, yeah.
We need to fix that, right?
Yeah, we kinda do.
Um, okay, so let's do the append. How do you do an append, Marinho?
Well, append is a monoid, so you can start with those cases. Those are trivial, right?
Okay, so you're saying append. We are appending lists, right?
Yeah.
So I have, okay, empty list. Oops. Appended with empty list is an empty list, and that's a fact. Cool.
That is true.
If we have a list with something and something else.
Yeah, you're actually missing the. You have the trivial case, which is append of two empty lists is empty.
Mm-hmm.
But then you have the non-trivial identities, which are append of an empty list and something else is that something else, and
Oh,
vice
you're
versa.
right, you're right. So if this is out and boom, not what I wanted. Out that. Okay. And then if we have things that are both with things inside, right? Oops. What should we do?
Well, technically, actually, you don't need to destructure the second list.
Mm-hmm. So second, I have a feeling this is just append on tail one. Second, and H1 out or something like that. Not 100% sure.
That's not quite it, because this recursive append is not going to produce the output for everything, right? It's going to produce an intermediate output, actually.
Really? Which
Yeah.
intermediate output is that?
It's going to produce the list that has everything except the first element.
I don't follow, I think. Could you go for like explain differently, I guess?
Like append of tail 1 and second is going to produce a list that has all the elements of tail 1 followed by all the elements of second, but not age 1.
So this is like, I don't know, mid.
Let's see. Try to do this.
Okay, what do we do next, Marin?
um, we need to do just a unification, an equality, which we don't have as a primitive, but that's
We don't have
oh,
equality?
there's a trick we can do actually. If you destructure the out, in fact.
We don't have equality. That's trash.
No, we don't. But there's a workaround. If we don't need a second call, we just destructure the out and say age one pipe mid.
Yeah, I'm still not getting why we need this intermediary step at all. Like, I know this is essentially doing the same thing as this, I guess. Why do we need this?
Because that's going to append the tail. We are just appending the age one at this point.
Okay, so we have a head and the tail of the first, and we have the entirety of the second. We want to append just the first, you said.
Yeah.
So then we just do it like this. So now we
Yeah.
need to call ourselves again, but Yeah, isn't it like this then?
Yeah, this should be enough. This should be enough.
Like this. Okay, we don't have conjunction, so I'm gonna have to comment this. Append, like so. It did work. It did work. Okay, so what are we saying is that, man, I know this is a simple program, but I'm still confused about this.
Margeta, look at this. This is beautiful.
Let me see. Wait.
Magenta, try to explain to me this definition of append, please.
Let me see. So append. Let me start. So if you have two empty lists, then it's empty. If I have one empty and one out, then it is out. And the other way around, same thing. But if you can split the first into head and tail, that means that you have more than one element at least, and you have a second, then the third argument, which is the output, should be the initial argument and some intermediary recursion step that is defined with a mid. So oh, this is pretty clear. I can understand.
I'm having a problem understanding what the mid is doing here.
It is just the intermediary step of the recursion, right? So it's the out of the second iteration and so on until it finds the empty case, and then it just rolls back with
And
the
then at the end, we're gonna the final mid is gonna be this one,
yeah.
and then we keep concatenating that. Okay, I see. That's actually pretty clever, and it works as you see here.
That's very impressive, actually.
Uh, it actually works. Okay, so we don't have more time. I'm gonna finish the recording.